DataForge is an autonomous data agent that transforms raw tabular data into AI-ready datasets. This demonstration showcases our ICDE 2026 paper by Xinyuan Wang and Yanjie from Arizona State University. Traditional data engineering is manual, time-consuming, and requires expert knowledge. DataForge automates this entire process from cleaning and feature engineering to validation with no human intervention. Let's walk through the interface. On the left panel, we have our data input controls. You can either choose a dataset from the server dropdown or upload your own CSV, Parquet, or HDF file. Today, we'll use the Garment Productivity dataset, a factory production dataset with 1200 records, missing values, and mixed data types. After selecting our dataset, we click Inspect Columns to detect available features. This populates the target column dropdown. We select actual productivity as our prediction target. Next, we select the downstream task type. We choose regression since we're predicting a continuous productivity value. Below that are three key parameters. Max actions controls how many transformation steps the agent will attempt. We'll use 5. Minimum improvement sets the threshold for accepting changes. We use 0.005. And time budget limits how long the agent runs. We'll give it 5 minutes. There are also advanced options, but we don't need to touch those. The defaults work well. Finally, the big orange Run Agent button starts the autonomous pipeline. DataForge now executes its autonomous pipeline through multiple stages. First, data cleaning. The system automatically handles missing values, detects and processes datetime columns, and removes incompatible data types, all without manual specification. Next, hierarchical routing. Level 1 routing analyzes the dataset, structure, and determines the appropriate task family. Level 2 routing then selects the specific method, in this case, LLM-based feature engineering. Now the core loop begins. The large language model generates candidate feature transformations, mathematical combinations of existing features that might improve predictive performance. Each candidate goes through grounding validation. The system checks that proposed operations are safe, executable, and schema compatible before applying them. Valid transformations are then evaluated using cross-validation. The dual feedback loop is now active. The inner loop ensures safety through grounding, while the outer loop measures performance improvement. The agent accepts beneficial transformations, rejects harmful ones, and continues iterating. When no further improvement is detected, it stops automatically. This entire process runs without human supervision. Now, let's look at the results on the right panel. First, the decision sequence table shows the step-by-step history. Step 0 is our baseline score. Each subsequent step shows the action taken, the method used, and whether performance improved. Below that is the LLM generator report. This is the key transparency mechanism. It explains in plain English what DataForge did and why. The report describes each transformation applied, which features were modified, and the performance impact. At the bottom, we have the download button for the process dataset. This CSV contains all the original data plus newly engineered features, ready to use in any machine learning framework. Now let's examine the results and understand what DataForge accomplished. For the garment worker productivity dataset, the system generated 59 engineered features, but found that none improved the performance of baseline score of 0.443. This demonstrates intelligent rejection. DataForge recognized the original features were already optimal and stopped appropriately, preventing data degradation. This fail-safe behavior is essential for reliability. The system doesn't degrade data quality in pursuit of marginal gains. It recognizes when the data is already well suited for the task and stops appropriately. Now let's look at the results of running the ionosphere dataset, a radar signal classification task with 34 features and 351 samples through DataForge. Here, transformations do help. The decision sequence shows that candidate evaluation was successful. Let's examine what happened. The system evaluated 20 candidate transformations on this radar data. Watch the score progression. Candidates 0 through 5 achieved F1 scores of 0.9422. These applied basic unary transformations like square root and logarithm to individual features. Candidates 6 through 12 scored lower at 0.9396. The system recognized these were worse and marked them for rejection. Then candidate 13 achieved 0.9426, the highest score. Why did candidate 13 win? Let's understand the reasoning. Radar signals often contain nonlinear patterns and noise. Candidate 13 likely combined complementary transformations, for example, applying logarithmic scaling to compress high-amplitude signals and square root operations to normalize skewed distributions. These transformations help the random forest model by making feature relationships more linear, reducing the impact of outlier signals, common issues in ionospheric radar data. Candidates 14 through 19 were also evaluated but scored lower, confirming that candidate 13 was indeed optimal. The key insight, DataForge didn't just randomly apply transformations. It systematically generated 20 candidates, rigorously evaluated each through fivefold cross-validation, and intelligently selected the single best transformation based on empirical performance. This demonstrates DataForge's three core principles in action. The entire pipeline, from cleaning through routing, grounding, feature engineering, and optimization, ran without any manual intervention. Every decision was validated through grounding checks and dual feedback loops, ensuring reliable operation without human supervision. The simple interface and natural language explanations make advanced data engineering accessible to everyone. DataForge represents the practical realization of an autonomous data agent. The full paper is available at this link.